All right, so as you know, and as you can see, got the exams graded. You probably saw it in Moodle. So I'm going to pass these back in just a moment. We'll talk about them, and we might get to a bit of solubility afterwards. As you can see, also the average grade was just a hair under 80. It rounded up to 80, essentially. So felt like you overall did a bit better. So well done. Yeah, so I'll pass these back out, and we'll have a discussion. All right, Patrick. Madeline. Macy. Natalie Johnson. Ian Schultz. Danielle Church. Lily. Andy Beats. Essie. Jonathan Perky. Matthew Wire. Jake Lee. Jack. Braden. Stephen. Jacob Sosky. Tyler. Elise. Brooke. Everybody got theirs? All right. What's that? You can see how it happened. Yeah. Yeah, so as you see, number 3, I had people looked like they were trying to answer it, but then never indicated one or the other. So I was like, well, let me just see if I can give an extra chance there. All right, so let's get to it. All right, so to start with the kind of short answer parts, and overall, one thing I'll say is like reflecting on it, I realized the electroneutrality equation was kind of like the thing to know throughout the whole exam, and I didn't plan for it to be that way. Didn't really realize that until like I was grading it. I'm like kind of finished with it. So hopefully, I gave you at least enough of a hint that the last problem kind of wrote it out for you a bit. So maybe you got to see that and look backwards if you needed to. But starting from problem 1, I said write out the electroneutrality equation for a simple acid HA in pure water. And I think everybody did pretty well on this. So the electroneutrality equations, we're going to basically sum all the cations on one side and anions on the other, set them equal to each other. And this, of course, has to be in equivalent charges, essentially, or charge equivalents. And typically, if it's just a single charge thing, we just put brackets on it and say that's the molar amount and call it good, right? So in this case, the different things we're going to have in solution will be protons, OH minus, and A minus. HA does not belong here because it's not a charged species, right? So it's there, but it doesn't matter for our electroneutrality. So the convention is to do cations on the left, anions on the right. Doesn't really matter too much. If you reverse that, it's still equal, right? So this should look like this. Next up, we do something a little more complicated with ammonium chloride, NH4Cl, and sodium acetate, Na, and we're just going to abbreviate the acetate to AC. So this should be like our NaA, so to speak, just saying it's acetate. So that'll be sodium is there, acetate should be there, AC minus. And then we've got, of course, H plus and OH minus because we're in water. Then we also have ammonium ions, NH4 plus, and Cl minus from the ammonium chloride. So that part might have been a little trickier if you didn't recall kind of what exactly was going on there. So all told, we should have on the left H plus our sodium plus our NH4 plus, all that equal to the remaining ions. Okay. Any questions, issues there? All right. So then we have the true or false question that says the HA equivalence point is defined as the pH that will result from adding exactly 1 mole per liter of HA to pure water. This is false, so hopefully, even if I'm not grading yours today, hopefully you got it right again. But we define the HA equivalence point as if we, as the pH where essentially we added HA all as HA. It's not a specific amount, it's just we added that acid exactly as HA. Or we could say we started at NaA and added exactly enough strong acid as the total amount of the A total in solution to bring it from the NaA equivalence point back to the HA equivalence point. So there's a couple ways we can define it, but it's never in terms of a specific amount of HA, the exactly there is kind of the point. Okay, problem number 4, we say consider a scenario where you're titrating a simple acid, HA, with a strong base, NaOH. After adding some base, list the different ions in solution. So a little bit like what you saw me do just a few minutes ago with just even putting this stuff out there, what's in solution. And do note that I put ions. I don't think if I counted you off, it would be only a tiny, tiny bit for listing non-ions, but I did ask for the ions, right? So that means it's charged. So technically water's in there and HA is in there, but those are not charged, so I'm not listing those, not including those as part of my list. So we should have A minus, OH minus, H plus, and of course Na plus, and that should be it. So then part B asks, if we add, or as we add NaOH, how does that sodium concentration that we're adding relate to the Cb minus Ca equation, so the net strong base? And I was hoping that you guys would recall or recognize that while we do have this formal Cb minus Ca equation, and essentially what it equates to is all of the things that participate in some sort of acidity, right? So if we flip back to the formula sheet, I think I even gave you that. So everything on the right side, it would look something like this for this scenario. The fraction that is in the A minus, so alpha 1 times A total, plus our OH minus. It's essentially the electroneutrality equation, except we've readjusted it. And if you recall, we readjusted it to put all of the spectator ions on the left. So essentially in this system, the spectator ions consist of exactly sodium. So the left side, we've been calling it Cb minus Ca, but when we first derived it, we started from an electroneutrality equation and said, everything that's not changed by pH, we're going to shove to one side. So the left side over here is just simply not changed by a pH change. So we've taken our electroneutrality equation and set everything that is changed by pH changing on the right and everything that's not on the left. And it turns out that is very convenient. So that means essentially our sodium concentration, because we don't have any other spectator stuff, is simply equal to Cb minus Ca. You could also write that it's equal to this guy up here. So I was hoping that you would recognize that the only source of sodium is this strong base, and so whenever you're adding base, you are also adding the sodium. It does not mean that the sodium is equal to OH minus, right? Because there's other things that are taking away OH minus as it's being added. So just like you see right here, if we add some NaOH, net strong base, well, yeah, OH changes, but there are other things that are changing also for every sodium hydroxide that we add. So it's not exactly that it's equal to sodium. All right. Any questions or issues with that? Okay, problem 5. We had you take the electroneutrality equation and formulate a left-hand side minus right-hand side equals 0 equation. So I wanted you to derive the equation. Wasn't trying to get you to solve it. Wasn't trying to make you do anything too fancy. Just write it out as if we were going to solve a problem like with Solver or something. So that was the hope. And we had a system with 2 monoprotic acids, HA and HB, in pure water. And we also said that we know those dissociation constants, and we know Kw for water, and the total acid and total, the total concentration of each acid. And kind of reminded you we are given the formula for the alpha fractions in the back. So the deal is, for the electroneutrality equation, we want to know, first of all the ions, right? And then work from there to get left-hand side minus right-hand side. So let's start by listing all the ions. We have H+, we have OH-, we're going to have A- and B-, and really that's it, right? So for our electroneutrality equation, we're going to say this will be H+ on the left equal to OH- plus A- plus B-. Now, as the problem reminds us, we can take this and say left-hand side minus right-hand side equals 0. So I could just do this, say minus all that equals 0, right? So I'll write it out one more time just to be a little more clear. But this is kind of the point of that step. Okay, so we have that, but now it's not in terms of pH. And I asked for it to have that has H+ as the only unknown for a solution, given that we do know the Ks and the total concentration. So that means we want to try to get each of these guys in terms of H+ or one of these other knowns. Okay, so that's the other part of this challenge. So some of you did okay and got part way there, but did not quite get all the way there for these spots. So from here, what we want to do is recognize that OH-, we have a term for that because of the water's constant, right? Kw divided by OH-. Can substitute in here because the Kw is equal to H+ times OH-. So we convert it, substitute it, and now we have something in terms of knowns. We're going to do the same thing for A-, and in fact we did that just a minute ago. We looked at that was essentially A- for that scenario. So we can do the same thing here. Also, instead of just putting the alpha, which would be fine, it's still not in terms of the knowns and unknowns. So really what we want to do is substitute the alpha in there. And I did give you that in the back, something that you could probably derive. But what we can do is say the A total times this alpha fraction And one way to write the alpha fraction is the Ka divided by H plus Ka. You'll note if you divide the top and the bottom by Ka, we've also seen it in that form before, where it would be 1 over 1 plus H plus over Ka. So you've seen that stuff before, you've derived it before, but I went ahead and said, hey, look, check the formula sheet, it's over there. So hopefully you were able to recognize that. I think a fair number of you were. And then we can do the same thing with the B. Okay, and that's what I was looking for. That is equal to 0. That make sense? All right. Great. Okay, so problem 6, I think it gave a few people some problems, in part because we had talked about it a bit, but perhaps I didn't emphasize enough what happens with the HCl, the strong acid. And so a few of you ended up doing something kind of smart to use your graphs to tell you something about the later problems, the B, C, and D, but had the graph wrong, so there's some trouble. So I tried not to take too much off if I saw you were doing something smart there, but okay, so let's take a look. So part A says sketch and label 2 systems in the space provided, and the 2 systems are, from the problem, HCl with a pKa of negative 5.9, which is a strong acid, to the weak acid, acetic acid, with a pKa of 4.8. And the first mistake that a lot of people made is didn't pick up on the fact that there's a negative here and not here, right? So the negative was actually quite important for these very strong acids. You would have an equal amount of HCl and Cl minus, so HA and A minus, way off in a negative pH. So we don't actually see that in real water because it's so extreme, but if we could, it would be out there. That's the deal. So when we sketch these, there's a few things that I'm looking for. One is that the total concentration AT has been accounted for. That means we're starting essentially right here. So whatever species are going to be around, they're going to max out here. I'm going to start with acetic acid. This is a little more normal. We're going to say this is at pH, where our pK, they're going to equal the AC minus and the HA, we'll say HAC here. I'd like to see those labels to know that you are understanding where you're supposed to have the protonated versus deprotonated versions. And then where they cross. Where do they meet? Well, pKa 4.8, so pH is 4.8 is where they're going to meet. And it's about a third of a log down. Right, so it should look something like that. So we can draw these something like, well, that dot disappeared. It'll look something like that on this side, and then something like that over here. Okay, so if you drew something like that, I was pretty happy, recognizing about the right height, the right labels for the protonated, deprotonated, and get a slope that's approximately plus or minus 1 once we are tailing. Now, the HCl, like I said, we'd have to draw it pretty much off screen, somewhere over here for the pKa where they meet. And that means that our HCl shows up almost nowhere. But I was hoping you'd recognize that it should show up a little bit. So just like this graph, if we look at our pKa's around 5, and then we move 5 pH scales to the right, we will also move 5 pH scales down and find this guy. So if we take our HCl, which is basically going to, this equilibrium point is negative 6. So if we take 6 logs over we would expect 6 logs down before we see it. So if we take this, we're starting at a -3, go down 6 logs, somewhere right around here is where we will start seeing some HCl. And it should be in a straight line, getting even smaller as we go. So theoretically, you should have a little line there. I think I maybe counted off 1 point if you missed that, but it wasn't a big deal. Right, so this should be our HA, or in this case HCl, and then basically everything else should just be the Cl minus. So that's kind of what I was looking for. A lot of you got it very, very well done to recognize that it's just Cl minus the whole way. Didn't catch this, and maybe I'm being too picky to even expect that from you. But a few people did get all of that correct there. Okay, does that make sense? Good on that? So it's not technically true that there's none of it there, but there's just practically none of it at most pHs. Okay, so then the next problem, part B, says using the acidic solution approximation, calculate the pH of the HA equivalence point for a solution of 10 to the minus 3 moles per liter if the pKa is negative 5.9. I think I also, I think in class I might have said also assume the strong acid. I think I might have clarified there. This is basically the type of problem you saw in general chemistry where you said you add X amount of acid, what's the pH? Where you just assume that every one proton that you add, basically that the H plus is going to be equal to pretty much the amount of acid that you add, A total. This is going to be true if we flip back at this graph. As soon as we add any HCl, practically all of it at any pH range is going to be released as H plus and Cl minus. So it's effectively completely dissociating at any spot. So if we added 10 to the minus 3, that would mean that H plus is approximately 10 to the minus 3, which means the pH should be 3. Okay, so that was my hope that you'd see that. Part C says use the acidic solution approximation and the weak acid approximation to calculate the pH of the HA equivalence point for a solution of 10 to the minus 3rd moles per liter of acetic acid if its pKa is 4.8. So this one, if you look toward the back, this approximation is given, and it says that the H plus is approximately going to be equal to the square root of the Ka times the total acid. So that would say we've got the square root of 10 to the minus 4.8 times 10 to the minus 3rd. Now, I think a few of you also maybe double checked this or looked at this to say, well, we just plotted this, and you might be pretty confident that you could find that HA equivalence point because you knew it's where these two P lines cross, right? So that's a pretty good approach as well. You should get something, if you take a look at that pH, it should be right around or just below 4. It turns out that when we do that, this value is 0.000126 moles per liter, and I asked for the pH. That'll translate into 3.9. So looks good. My drawing was decently to scale. Okay, any issues? I think mostly if there were issues on these problems, you were accidentally making it more complicated than it needed to be. Part D, especially true there, and we did cover almost exactly this problem in the homework, so I was hoping you'd catch on to that. So it said, what is the pH at the NAA equivalence point for the HCl system, given that the pKa is negative 5.9? Gave you the hint to kind of remind you, hopefully help you to say one's very simple. So the HA equivalence point is essentially what happens if we simply add only the NaA version. And in this case, it's NaCl. You've seen that a lot. We talked about it. That's adding table salt, right? And we know that that's not supposed to, and I see a little facepalm action. And yeah, so that shouldn't change the pH any. So that should mean that pH of the NaCl, so the NaA equivalence point, should be 7. If we go back and look at the graph, I know some people, like I said earlier, made a mistake on this graph. It's unfortunate, but if we, if we look at this, our typical way of defining when do we find the NaA equivalence point, it doesn't quite work for this graph. So we kind of have to recognize, or let's see, is it that it doesn't quite work? Yeah, I think, yeah, because this is definitely not the correct pH. I think that's what it would be. So normally for like a weak acid or something, where the lines cross works, but for extremely strong acids or bases, I think that the equivalence point thing doesn't, that approximation doesn't help us. So anyway, if you add NaCl to your water, it's not going to change the pH. All right, any questions or issues on that? All right, so this one I was looking for interpretation of the titration curves. So we have a titration of an unknown acid that's performed yielding the following plot. So based on the figure, I asked you to answer a few questions. First of all, approximately what pH is the HA equivalence point? So the HA equivalence point is going to be where we start the, essentially where we start the titration. And that's actually given as the 0 point. That's kind of defined for us. And it even says pure conjugation conjugate acid endpoint. So all we really have to do to find the pH for part A is to estimate where that shows up. And I was looking at it and I gave it the arbitrary value of 5.8. If you got anywhere near that, maybe 5.5, maybe 6, I should have given you credit for that. So if you're within, I don't know, plus or minus 0.5 of that, what I drew here is not even that great to scale. Maybe it's here, something like that. You get the idea, right? Has to be related to that point. So then part B says approximately what pH is the NaA equivalence point. And again, the key here is to recall, or to even read, that this is the conjugate base endpoint. So if we have NaA, A minus is the conjugate base. So this would be the NaA equivalence point, and the conjugate acid is the HA, right? So the HA equivalence point. Of course, we are on a graph that is a little bit flipped compared to what we often look at, so we have to go from here to the left. So I took a line this way, and in my own notes during the exam, it looked a little more like 10.5, but today it's looking more like 10. So anywhere near 10-ish, 10.5, maybe even, if I counted you wrong and you did like 9.7, come talk to me because I'll give you credit. But this is what I wanted you to do. Take a look, make sure it's up there, kind of, if you drew a line across, it was something like 10. Okay, and maybe I eyeballed from this dot, and then today I'm looking like maybe it's slightly under that, whatever. If you got close, you should have gotten credit. So then the next part says approximately what pH was the pKa of this acid. So this one, you'd have to remember that the pKa occurs when we get exactly halfway between our two endpoints, but that's halfway on the scale of how much net strong base we've added, right? So that's halfway in this case, on the x-axis, that's not halfway pH-wise. So if you half to the pH, if you took 10 minus 6-ish and said, okay, it's between those two, that's not going to get you the right answer. We actually have to go on the x-axis here and go something like right there as the halfway point and draw across from there and say maybe that's 9-ish. I think in my initial notes I said maybe 9.5, but I'm a little more convinced it's about 9 today. Okay, so if you got anywhere around 9 for that answer, should have been counted as fine. Finally, the last question says, what is the total concentration of the unknown acid A total? In this one, hopefully you recalled, we define this, and this is actually how the titration works. This is the N total here. Right? It's kind of, in a way, written on there. In this case, I maybe took from a different graph, and this was, ammonia or something, so it's called N, but that's your key, that's your hint, and this should just be simply 0.01 moles per liter. That is how we define how to interpret the titration. Actually, it goes back to that true or false question, right? It's like, how do we define one of these equivalence points? Well, it's when we've added that same amount of the conjugate acid or base to it, we shift from one to the other. Okay, so when we've added that amount of net strong base, we go from the HA to the NAA equivalence point. Okay, any questions? So again, I think if there was trouble, it was probably overcomplicating it, unfortunately. Okay, so the last question was kind of like, let's practice this solver Excel thing, but just do a little bit of it manually. And I tried to grade this in a way where part A, it would have been pretty clear to me if you had set it up correctly to get answers that were pretty close. But then B and C, you had to interpret based on your answers for A. So even if you got the wrong answers for A, I tried to look at the thought process rather than the numbers you gave me, because it would depend. If you got part A wrong but interpreted them right, that means you should get credit for B and C. Okay, so the deal here is we want to do the left-hand side minus the right-hand side equals 0, that sort of setup, and it's kind of written here almost already for you. So we should say from the electroneutrality equation that we'll have an equation that looks like this. H plus minus OH minus minus A minus equals 0. Then that would be, we could put it in this form, of course, to say that's minus alpha 1 A total minus, oh, sorry, I'd do the OH1 first. So KW over H plus minus the alpha 1 times A total. Okay, and in a way, you could have read that from here, right? And all that set to 0. So what we needed to do when we were given a few inputs here, we needed to essentially solve for this equation. We could go a little further and say this is 10 to the minus 14th was given. The H plus here, this was going to be one of the 3 conditions that we tested, right? So that'll change each time. So you're gonna have to change that in your calculator each time you solve it. But we could also include kind of the same deal here, A total. That was also given the HA concentration. This should have been kind of treated as A total here. And then multiply this by the Ka, divide it by H plus plus Ka. Okay, so the challenge here was to recognize that what I'm asking you to do is to calculate this to see how close to 0 we got, right? And I think almost all of you had that process correctly. So for pH 4, what I got when I did this in Excel was 9.09 times 10 to the minus fifth, excuse me. The next one at pH 7, I got negative 9.9 times 10 to the minus fifth. And for pH 10, I got negative 2.01 times 10 to the minus fourth. So chances are good. So I counted this part A as a total of 10 points. And chances are, even if you got something wrong, I didn't count much off. So if I saw you had something that looked like a calculation mistake, maybe I counted a point off. If I saw that you were not even in the ballpark, I would have counted a little more off. But in general, if I saw that you were attempting something like this, I was reasonably happy. So if that doesn't jive with what you see on your paper, you're welcome to talk to me about it. But this is kind of, I was expecting something like this. And it's important that we get close enough so that we can make the judgment call about which of these is closest to 0, right? And which one, in what direction are we going further and further away from 0? That's kind of the thing we need to know in order to answer part B. So based on these 3 guesses, what's your best guess on the pH of the solution? Well, if we go back and look at these 3 numbers, we have 2 that are 10 to the minus fifth, and one's at 10 to the minus fourth. So the one that's 10 to the minus fourth, plus or minus, is the furthest from 0. So that's further away from 0 than the other 2. And then noticing that these 2 are straddling 0, so 0 should be in between them. That's my best guess, somewhere between those 2. So what I was hoping for an answer here is somewhere between 4 and 7. So literally on my paper, I think I wrote, how about 5.5? You know, that's kind of the notes I took as like, here's the right answer between these 2 numbers, and maybe a 5.5 as a guess. So then with that in mind, to answer the last question, it asks us, what would be the next 2 pH guesses you would make in order to find the 0? And so I was thinking that, you know, maybe pH 5.5, which was my guess here, and then halfway between that and whichever was closer, the pH 4 or pH 7. That's a little bit fancy. I didn't need anything quite that fancy, but that was just my thought. So I'll answer it 2 ways. The simpler way would be, how about 5 and 6? Because it feels like it's somewhere in there, right? Another way maybe we could do it is 5.5, then halfway between that and whichever pH 7 or 4 was closer. Okay, so anything like that was fine. And if you got some different numbers here and it was looking like the true 0 should have been closer between 7 and 10 based on the numbers you calculated, I was looking to make sure that that's what you were thinking for B and C, right? And hopefully I accounted for that accordingly. Or perhaps, you know, maybe 10 was the closest to 0, oops, and so maybe you had to guess up above 10, or likewise, maybe 4 was the closest to 0, and it was getting smaller and smaller as you go closer to 4. So maybe you say, well, maybe we went pi it, and so we'll check 5 and 2 or something. Whatever the case, if it jived with the process, I hope I gave you full credit for that. All right, any questions on that? Any issues? Okay, I want to start on a little bit of material for the next lecture. We don't have a whole lot of time, about half an hour, so probably won't even use all of that. but we'll just get going on it a little bit. Okay, so last time we talked a bit about solubility, kind of following from the metals conversation, and say, okay, well, let's talk a little bit about precipitation. We took a look at this cool example of lead iodide, ended up crashing out when in the video they added something that was like turned really strongly yellow. Then they heated it up to dissolve it again and just let it slowly crash out with like what looked like a little snow globe with gold snowflakes, right? It's a pretty cool little video. Neat to watch that. Really showing in a few things about precipitation reactions in that equilibrium. That one, it can be temperature dependent, as you kind of know. You heat up, if you're going to make good old southern iced tea, you heat up your tea and the sugar dissolves better, right? You probably get that. You know, if you try to add sugar to cold brew coffee when it's cold, it doesn't have the same effect as if you add it to hot coffee, right? Okay, so there's a few things about that, and I'll even come back and mention it later about, you know, crystallization and things like that. But overall, what I wanted to highlight is this ion activity product. When we talk about this equilibrium equation where we have some solubility, it's going to be the products over the reactants, and the reactants are a solid, so it kind of goes to 1, right? So maybe it's A times B, something like that. This just goes to 1, and so it's essentially the solubility product is equal to the concentration of A times the concentration of B, if our solid is AB. Something like that, right? And that means if we just take the two concentrations of the things that we're interested in, multiply them together, we get our solubility product. Of course, sometimes we might have to take a little more care. So if we had an imaginary, I don't think this would be solid. If we had something like Na2SO4, I think that would probably dissolve very well. But if we put enough to make it precipitate, remember that the solubility product for that, we would have to have sodium squared because it has the 2 there, right? Because we're going to have 2 released every time. So just keep that in mind. We're going to have the appropriate use of our equations, but assuming we do that, we're okay. So don't want to get too distracted about that, just, you know, side note there. Then we can take a look at this ion activity product, that right side of the equation, and compare it to see whether or not our current condition is at equilibrium, or if it's going to be approaching it, or, you know, where is it with reference to equilibrium? Are we going to not have any solid present because it's smaller than the equilibrium constant? That's certainly possible. Add a little bit of sodium chloride to your water, it's probably all going to dissolve. Our ion activity product is much lower than the solubility product. Okay? We have no solids present. If it's equal, we are at that point where solids are starting to precipitate, going to have some precipitation, some of it going away. If we are above the solubility product, that's when the gold dust starts precipitating and we have solids forming. And that will decrease the amount of ions in solution until we reach that equilibrium. Okay, what we can do with that is pretty interesting. We can, first of all, make more plots, because who doesn't like plots? And let's just ignore the activity. You know, we can correct for that. But if we just take the solubility product for calcium sulfate as simply the K is equal to calcium times sulfate, one thing we can do is plot that on a calcium versus sulfate concentration plot. And with that type of plot, we can find a range where an area on that plot we are precipitating, and for the rest of it, we just have no solids present. So if we plot it in that manner, we can see, we can draw a line right here that says anything above and to the right of that, we will have solids. Our ion activity product is greater than the solubility product. Solids will be present. On the line, we are right at that verge, and we can say maybe precipitation begins or something. You know, that's kind of right where it can start being noticeable. Anything below that, it's just all dissolved. Okay? So then we can say we have a few different things in practice that we can consider. What if we have some other source of calcium or sulfate that we add to the solution? You know, we might be considering we have a little bit of calcium sulfate that we dissolve. Maybe it lands right here based on some amount we dissolve. Okay? We add a calcium sulfate salt, that exact amount. Let's make it a little more precise. If we're adding exactly calcium and sulfate, they should be at the same concentration, right? So let's take 10 to the minus 3 and 10 to the minus 3. So we've added 10 to the minus 3 moles per liter of CaSO4. Okay? So we end up at that spot. Make sense? Just how it's going to work. Now, what happens if we have some other source? So let's do this. Let's say we have some other source of calcium that would raise us somewhere else, right? So we might end up in a spot where suddenly we are precipitating because one of these has increased. We could add some and it doesn't quite get there. Of course, we could have some spots along the way. Nothing happens. But as you can see, this is what we call the common ion effect. So if you're ever dealing with doing some chemical analysis in seawater, for example, and you have to have a buffer in your solution and blah, 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 you add in the seawater and suddenly things start precipitating and ruins your method. Well, it's this common ion effect. There's too much concentration of something and it's throwing your chemistry off. Likewise, we've got Le Chatelier's principle. That's just meaning we can push these equilibrium one way or the other. So if we did go above it, well, we're going to start precipitating until we get back down to a point. And in fact, if we just had this scenario where we had the addition of some other source of calcium jumped us up right there, what's going to happen is as we precipitate, we're actually going to be removing some sulfate too. So we will actually travel, as we start precipitating, we're going to travel back this way and end up here. So if we see that, that's actually a way that we can remove sulfate by adding calcium. This is something we use when we're doing hardness removal, actually. And in that case, we're typically trying to remove calcium. But we could do something like that to remove the other thing by overwhelming it with that common ion for the other species. Okay, does this make sense? This is kind of a simple form of it. We're also going to take a brief look at the fact we can kind of do a similar thing with pH and scope out at what pH are we going to have precipitation. It's very important for things like coagulation or cases where we are intentionally precipitating some stuff. I think we'll go through this example, see how long it takes. Maybe we'll get to that last little bit that I was talking about. But let's take a look here. So if we want to determine the solubility product from data, if we take stannous or tin fluoride, SnF2, if we add that to pure water, we have a solubility of 0.012 per 100 milliliters. 0.012 grams per 100 milliliters. Using only that information, see if you can calculate A, the solubility product, KSO, for this stannous fluoride, and then B, the solubility of stannous fluoride in a solution that originally contains 0.8 moles per liter of sodium fluoride. So that common ion effect. So give this a couple minutes and see if you can at least piece together A and then give some thought to B, how you'd approach this. We'll take a look at the solutions together. All right, so if you're anything like me, you probably had not a good idea what tin's charge would be, because we just don't see it very often. But the F's should make that a little obvious. F is right above chlorine, and we kind of know that we always show, those halides always show up as a -1 charge, right? So if F is a -1 charge, which it should be, and it is, then we've got two of them. That means the tin should be in a 2+ state. And there's a pretty good chance tin can probably be in a few different states. At any rate, the overall balance here for the solid in equilibrium should be SnF2 in equilibrium with SN2 plus and 2F2 minus, 2F minus. So as I mentioned a minute ago, we have to remind ourselves that the solubility product should be then SN2 plus the concentration of tin times the concentration of fluoride squared, because the 2 there. Okay, so that's just a little side note. Hopefully you got at least that far. To continue that answer, we can take, and maybe I'll write this a little larger for you. We can take the amount of mass per volume. It was 0.012 grams in 1/10 of a liter. So we can multiply that all by 10 to get it per liter if we wanted to. 0.12 grams per 1 liter might be a nicer way to write it. And then take that and then account for the molecular weight of the tin fluoride, and that should get us to, let's see, is it, yeah, times the molecular weight, or excuse me, that's divided by. That should get us to 7.66 times 10 to the minus 5 moles per liter. It just left it in moles because I converted to, you know what, I'm just going to write what they wrote. They didn't do this part, so just going to fix that. Okay, but as you can see, you could divide everything by the volume and get to moles per liter if you want. Okay, so that's, and they just do that in the writing, so I don't know why I'm talking about it. Okay, so for each SN2 plus, there are 2F minus. Like I said, now we have that information to calculate the solubility product. So we know we can calculate if there's that many moles or this many moles per liter, then we would also say this is going to be the same concentration as SN2 plus, and we could find the fluoride concentration should be twice that. So F minus then should be 2 times 7.6. It's what, going to be about 1.5-ish, let's see, they have it, 1.553 times 10 to the minus 3rd moles per liter. Okay, so with that, then they can put it into the equation up here and find the value, right? Given that, they find the solubility constant is 1.8 times 10 to the minus 9. Okay, so that's part A. Does that make sense? Get that far? Hopefully, or close. Okay. Part B. So let's see. So picking up right here, so note that because we use concentration, we could correct for ionic strength if you want to. Part B then says if a solution contains 0.8 moles per liter of F minus, well, the concentration of SN2 plus, and thus the number of moles of SnF2 that can dissolve, would be essentially here what we're going to do is we're going to take that 0.8, essentially they're going to set up the ion activity product. So they're going to say that the ion activity product is equal to SN2 plus times F minus squared. And what they've done is they said another way to write this is to use some sort of substitution value. So in this case, we can say the ion activity product we could write as, I'm just going to write it as S because that's what they do down here, times S squared. 2s squared, because there's twice as much fluoride. Okay, so that was what we looked at a minute ago. If we just simply say this guy is S, then we could say the formula is S times 2s squared. So when we do that kind of substitution, we can rewrite this to say if we have plus 0.8 moles per liter of F minus, then the ion activity product is going to be equal to S times the 2s that we know is there already plus the 0.8 moles per liter, and square that. So that's what they're doing right down here. And we know, rather than writing that as the ion activity product, they were asking, well, how much can dissolve is sort of the question, I think, right? Said, find the solubility. Okay, so yeah, basically how much is going to dissolve. So instead of writing that as the ion activity product, I think I probably should have written this as the solubility product. So that'll give us that'll let us answer the question how much tin dissolves, right? Because S is substituting here for tin. So with that, if we solve that for S, well, first of all, we know that we already solved for the 1.8 times 10 to the minus 9 equals that. Oops. Okay, so we can use a substitution method here to put all that in and then solve for S. This would be a bit simpler if it didn't have the square there, but as you can see, it's going to be algebra one way or the other. Okay, and they do that here. It says, okay, it's a cubic function, so maybe we use solver or fancy calculator or something. So we'll read it out. So note that one can assume that 2s is a lot smaller than 0.8, so basically we can probably just ignore that 2s that's in the function there and just square the 0.8, and it'll probably be good enough. So that gives us, essentially, if we write it out, then that's 1.8 times 10 to the minus 9 equals 0.64s, and then that means S would have to be 2.81 times 10 to the minus 9 moles per liter. Okay, so there you have it. We went from a solubility where I think it was about, yeah, should be, or does we how to say it? Okay, I'm just gonna read it out so I'm not confusing anything. This again illustrates that common ion effect. The solubility of stannous fluoride is more than 5 orders of magnitude smaller in 0.8 moles per liter of sodium fluoride solution than in distilled water. Okay, that's kind of the point. Okay, makes some sense there. Just kind of wanted to show you the ways we can manipulate some of this comparison between an ion activity product, what's going on in solution, and the solubility. Okay, so we'll pick up here next time with a little bit more metals, but then launch into some redox chemistry next time.